Hello everyone, I'm Siddharthan. This is the second deep learning project video in our channel, and in this video we will be working on the MNIST Handwritten Digit Classification using neural network. This is one of the basic and important use cases in deep learning, and this is an image recognition task, and working on this will give you an idea of how to handle image recognition projects. So let's get started. So first of all, let's try to understand what is the workflow that we have in any image recognition problems and as well as in this MNIST handwritten classification. So first is about data collection. So first we have to get this data set. So this particular data set is available in Keras itself. So in case you are working on some other image recognition task, you can search for the data set in Kaggle. Or if you are working in a company where you have to build this deep learning system, they probably will tell you an idea of where you can get that particular data. So the first part is collecting the appropriate data for your particular use case, and the next one is to process the image data that you have. Okay, so so we have seen like what are all the different image processing that we have to do in the previous video. So we have seen that what does the dimension of an image means, and we have seen what is meant by this pixels, and we have also seen that there are RGB images and grayscale images and so on. So the steps involved in image processing are, so in case you have images in different dimensions, so the one step would be to resize all the images to a common dimension. So that is one of the steps. And after that, in some cases, we will try to convert this RGB images to grayscale images. So you can consider this RGB images as colored images and grayscale images as the images, a black and white image which has only one color channel and so on. So these are some of the image processing tasks that we have. And once we have these images, we have to build the labels for these images. So once we have this image data as well as the label, we can split this data into training data and test data, similar to how we do this in any machine learning task. Okay, so we will train our neural network with this training data, and we will evaluate our neural network with the test data that we have. Okay, so once we have trained our neural network, so we will feed this data to this neural network, and this neural network will be trained on the data set that we have. So in this case, our goal is to give an image, and the neural network should tell us what that particular digit is. Okay, so the different digits that we have are from 0 to 9. Okay, so these 10 numbers, 0 1 2 3 all the way up to 9. So this is like a single digit detection neural network, so you can think about like that. Okay, and once this neural network has been trained, if you give an image of a new image, or the image that contains some number, it kind of recognizes what that particular image is. So this is what we are going to do in this MNIST handwritten digit classification problem, where the ultimate goal is, if you feed an handwritten digit, this trained neural network should tell you what that particular digit is. So this is the idea, and so this is the process we will be following. Okay, so once we train this neural network, once we evaluate it with the test data, we will build this predictive system where if you feed the image, it will tell you what that particular digit is. Okay, so let's get started. And so I'll just open my Google Colab now. Okay, so this is the MNIST handwritten classification problem. So the first step will be to import the dependencies that we need. Okay, so dependencies are nothing but the libraries and the functions that we need. So I'll make a text here as importing the dependencies. So if you haven't worked on any deep learning projects, or if you haven't trained any neural network like this, like you can understand this particular video, because I'm going about all the basics that we have. So don't worry if you haven't worked on any deep learning use cases. So first I'll import the Numpy library. So I'm importing Numpy as MP. And the next thing I'm going to import is the Matplotlib library. So import Matplotlib dot pyplot as plt. Okay, so this numpy library is very important in deep learning projects, because we have seen in the previous video itself that we will convert the image data into numpy arrays. So we need this numpy library, and then we have this matplotlib library. So once you have this numpy arrays, we can visualize this image so using this matplotlib plots. So once you feed that numpy array to the plots of matplotlib, you can see what that particular image is. Okay, and the third library that I'm going to import is cbound. So this is also useful for certain plots. So I'm going to import cbound as SMS. And the next library will be CV2. So CV2 is nothing but the OpenCV library. Okay, so this OpenCV stands for computer vision, and this is one of the important libraries that we have when it comes to image recognition tasks. Okay, and the next thing that I'm going to import is from google.colab.patches import CV2 I am sure. Okay, so this cv2 imshow function is just used to show an image, to display an image. So this is actually a function that is present in this opencv library, but google colab doesn't allow you to use this particular function that is available in the cv2. Okay, so instead of that, so they gave an alternative in this module google.colab.patches. Okay, so from this we can import the cv2 underscore imshow. So like if you are working on spider or pycharm, so you don't have to do this. So you can import this, or you can work on this like cv2.imshow. So you just have to import this opencv library alone. As we cannot do this in google colab, we are importing this as cv2 underscore imshow. Okay, and let's import another image processing library, which is pillow. Okay, so from pill, where pill stands for pillow, so from pill, let's import this image module. So this is helpful for us. And after this, let's import the deep learning libraries that we need. First, I'm going to import TensorFlow. So we will be working on TensorFlow and Keras. So let's import TensorFlow as TF. And now I'm going to set the random seeds. So TF dot random seed. Okay, so sorry. So TF dot set seed. So TF dot random dot set seed, and let's set the seed to 3. So you can give any values for this. And the purpose of this setting the seed is that, so when you're training a neural network, when you're feeding this data to your neural network, and once this neural network is starting to learn from the data that you feed, what happens is there are several values that randomly gets generated. So like let's say that there is some parameter that has to be given for this neural network, and in some cases these values will be generated randomly. So because of this randomness, each time you train your neural network, you will get different results. Okay, so even if you use the same data, so the accuracy values and other values may slightly change. Okay, so there won't be a large change, but they will slightly change. So when you set this random state to a particular number, so this changes won't be there. Okay, so this is the reason for setting this random seed. You can set any numbers you want. So if you give that particular number, you will get the identical result. So this is just like the random state value that we have in train test split function. Okay, and the next thing is, from TensorFlow, let's import Keras. Okay, so Keras is another important deep learning library. So the most important and the famous deep learning libraries that we have are TensorFlow, Keras, and PyTorch. Okay, so PyTorch is developed by Facebook, and TensorFlow is developed by Google. So Keras is just like it is a wrapper of these deep learning libraries. So previously it was difficult to build neural networks with this TensorFlow library. So they created this Keras library, which helps us to easily create this neural network. Okay, so we will use this keras, and in the backend there will be this TensorFlow. So after a point, TensorFlow included keras in their own library itself. So we will be working on the APIs that we have in keras. Okay, so we will be working on sequential and other layers and so on. So that is the idea of importing this keras. And then from keras dot datasets, let's import MNIST. Okay, so as I've told you, this MNIST is a famous dataset, and this is useful for someone who is starting to learn about deep learning. And this dataset is available in this Keras library itself. So we might have came across this breast cancer data, diabetes data, and these datasets are present in the sklearn library, right? So similarly, we have a few datasets in this Keras library. So and here we are going to use this MNIST library. So that's the idea here, and we will see how we can load this library. But this is the reason. So we are from this keras.datasets module, we are importing this MNIST. And finally, I'm going to import from TensorFlow .math import confusion matrix. Okay, so these are all the things that I want. So let's run this. So we have NumPy for NumPy arrays, Matplotlib and Seaborns for the plots and graphs that we want. CV2 is the OpenCV library for image processing task, and then we have the CV2 IMShow for displaying the image. Pillow is also used for image processing task, and then we have the deep learning library TensorFlow, and we are setting some seed for this TensorFlow, and then we are importing Keras, and from Keras the datasets MNIST data, and finally we are importing the confusion matrix. So these are all the dependencies that we need. So the next step is the data collection part. So I'll mention the text here as loading the MNIST data. Okay, so MNIST data. So this is basically image data from keras.datasets. Okay, so how we can import this data set is like this. So we have to give this so MNIST dot load data. Okay, so we have already imported this tf dot keras dot datasets. So instead of doing this, we have imported this keras dot datasets like directly. So first we have imported this keras, and then we have imported this keras dot dataset. So from this we have imported this MNIST and so on, right? So instead of that, from this TensorFlow itself, they are loading this. So they are basically the same thing. So we are doing this step by step, and here they have mentioned as one single step. So that's the thing. So we have to mention this MNIST dot load data. Okay, so that's what we need to do. And so once you load this, you will get 4 arrays, and the 4 arrays that you get are xtrain, ytrain, and xtest and ytest. Okay, so the thing here is this is an already processed data, so you don't have as raw images. So we have seen in the previous video, right? So in the previous video was about how to process the image data for deep learning, and we have taken a single image. So we have taken the single dog image, and we have seen what are all the different processing that we do. So we have seen that we have to convert this image into a numpy array like this. And so this is an example of a RGB image, right? Because we have 3 here, so 3 represents this 3 channels that we have: red, green, and blue. And these 2 values are the dimensions of the image, the width and height of the image. And the next thing is like so the other processing that we do is we have to resize the images. This is because if you have 10,000 images in your data, if all the images are of different dimension, then it is hard for the neural network to understand this images. So we have to resize the images to a common dimension. So in this case, we have used this pillow. So this image module, from that we have used this from this pillow library image module, we have used the resize function, and we have resized to 200 200. So this is another processing, and after that we have to convert this RGB image into grayscale image, so that we can save some storage space and the computation power and so on. Whereas in some case we have to work on the RGB images, but for this digit classification we can work on the grayscale images itself. And all this processing has been already done, and they have been stored in this MNIST data. Okay, so all the processing has been done, and they have also splitted the data into training data and test data. Okay, so we don't have to worry about that. So if we just go to this workflow, until this part everything is covered, from image processing to the train test split, all the things has been covered. But it won't be the case in all the things. So in some cases you will have only the images, and you have to process them and so on. So we will discuss about that in the upcoming project videos on how we can do that. But in this case, we already have the processed images, and the data has been split into training data and test data. Okay, so you have to mention the 4 arrays here: so xtrain, ytrain, xtest, and ytest. And so let's create them. So xtrain comma ytrain, and then xtest ytest, okay, is equal to MNIST dot load data. So we can see this function here. So we have this MNIST load data, right? So MNIST load data, so we have to mention the parenthesis. Okay, so when you run this MNIST dot load data, you will basically get 4 arrays, and those 4 arrays are nothing but this xtrain, ytrain, xtest, and ytest. Okay, so that's what they have mentioned here. So this is how you can load this xtrain, ytrain, xtest, and ytest. The only difference is that I have just used this caps for x and y, so that's the only thing, but the process is kind of the same. Okay, so let's run this. So this will load this MNIST data to these arrays, and you can also check the data type of this arrays. So we know that we have the keyword a type in Python in order to check the data type. So I'll give this as type of xtrain, and here I can see this is in the form of numpy n dimensional array. Okay, so this is just to understand that the images has already been converted to numpy array. So we don't have to do that again. So we have the numpy array, so images have been converted to them. And now let's try to check the shape of these arrays: xtrain, ytrain, and xtest and ytest, and then we will try to understand what these 4 arrays means. So shape of the numpy arrays. So this is the basically the data that we have. So I'm going to print. I'll just copy all these things: the xtrain, ytrain, xtest, and ytest. Let's put this here, and I have to mention this as xtrain dot shape, and ytrain dot shape. So I'll remove this parenthesis: ytrain dot shape, xtest dot shape, and finally ytest dot shape. Okay, let's try to understand what this signifies. Okay, so the value that we have for this xtrain.shape is 60,000 and 28,28. So what this basically means is your xtrain contains 60,000 images, and each image has a dimension of 28 into 28 pixels. Okay, so these are the value of height and width of the image, and these are the pixel values. So we have already seen about this. Okay, so if you consider this dog image, so it has printed like this, right? So what this means is like the height of this image is 200, and the x-axis value, which is the width of the image, is also 200, which is represented here. So here we have this 3. So what this 3 means is it has an RGB image, whereas we don't have that particular number here. So this means like this is a grayscale image. So xtrain is my 60,000 images, and like each image is so 28,28 is the dimension of each image, and this is a grayscale. All the images are grayscale images, and the label for all these images has been stored in this Y train. Okay, so let's say that this X train has the image as, let's say, 7. Okay, so we can see this particular image. So once we train our neural network, we will feed this image, and we will check whether our neural network can recognize this image. So we have this 3, right? So this image has been converted to NumPy array, and it has been stored in this X train. Let's consider that. And the label, so in this case the label is 3, right? So that will be stored in this Y train. So 60,000 represents my training data images, and the label for all these images are stored in this Y train. And then X test represents all my test data images. Y test represents the corresponding labels for all these test images. So that is how this data has been splitted. And if you see the count here, we have 10,000 test images. So the number of training data that you have is 60,000, and a number of test images that you have is 10,000. Okay, so that will be mentioned here as well. So you can see. So yeah, so xtrain is unit-8 NumPy array of grayscale images. So this is what I mentioned, because if that is an RGB image, there will be another value as 3 in this case, but we don't have. This is a grayscale images of 60,000 values, and all the values ranges from 0 to 255. So we know that all this value represents what is the intensity of the white color. In the case of RGB images, we have 3 matrices, and each matrix correspond to red intensity, green intensity, and blue intensity, right? So all the values in an image range from 0 to 255. So we know that, and all the labels are present in this Y train, and the values range between 0 to 9. Okay, 0, 1, 2, 3, all the way up to 9. And then in the test data, we have 10,000 images. They also in the 28 into 28 pixels, and sorry, height and width, and they also have the values between 0 and 255. As 0 means that particular pixel is completely black, 255 means that particular pixel is white in color, and the corresponding labels has been stored in this Y test. Okay, so this is the shape that we have, and you can see here. So this is a data set of 60,000 28 into 28 grayscale images of the 10 digits, along with the test set of 10,000 images. So that's what we have understood here. And so let's just make some text here of what is present in this data set, so that if you look at this at a later time, you can understand this. So let me put this as training data is equal to 60,000 images, and my test data is nothing but 10,000 images. Okay, and each image has some dimension of, so image dimension is 28 into 28. Okay, and grayscale, so these are grayscale images, right? So grayscale image means they have only one color channel. Okay, so unlike RGB images, which have 3 color channels. So this is the basic information of the data that we have. So as I've told you earlier, we don't have to convert these images into grayscale images, and we don't have to resize the images and so on, and we don't have to convert this to NumPy array. So all these things has been already done, and all this has been split into training data and test data as well. So until this part, everything has been already done in this data set. So we have to just try to see what are all the images that we have to get some basic idea, and after that we can train our neural network. Okay, so what let's do is let's try to print an image from this data that we have. So let's take one particular image. So printing, let's say I'm going to print the 10th image from this X train. So I'll mention this as print X train, and in this I'll say 10. So 10 is the index of this image. So which is basically it is the 11th image, because we know that in Python indexing starts from 0, right? So the image in the 10th index, so these are all the values. So we know that it is in the form of a NumPy array, and all the values range between 0 and 255, right? And we have already seen, once you have this in the form of a NumPy array, we can convert it back into an image, right? So let's see how we can do that. And I'll also check what is the shape of this image. So xtrain 10, so this is the image that we have worked on, right? So xtrain of 10 dot shape, so this will tell you what is the shape of this image. So it is a 28 into 28 image. So this is the height and width. So totally we have 60,000 images, and all these images have this particular dimension. So this is why I told you that all the images has been resized already, and all these images have the constant dimension. Okay, so this is the single image dimension. And now we are going to display the image. So displaying the image, plt.show, sorry, plt.imshow. So this plt.imshow is used to show an image. So we know that plt means the Matplotlib library that we have. And I'm going to show, let's say you can just mention any images that you have. Xtrain. Now it is in the form of NumPy arrays, and we are going to convert it. Let's say the index is equal to 50. Okay. And plt.show. So this will print my image. Sorry. So xtrain 50 and plt.show. Okay, and now what I'll do is I'll also print the label. So in this xtrain, I will take the image with the index of 50, and from this ytrain, and I will take the 50th label as well. Okay, so let's see. So plt imshow, which stands for image on plt.show, and here we will print the corresponding label. Okay, so print ytrain. So ytrain is my training data label, right, of 50. So let's see. Okay, so this is the 50th image that we have, and this is the label for that image. So you can just give anything here. So let's say that I'm printing the image with index 25, and I'm printing the corresponding label. So both the things will be same. So previously it was in the form of a NumPy arrays, and we are just converting back into an image to just check whether the image and the labels are correct. Okay, so this is the image. So this, we know that this is two, the image of the number 2, and we have the label as 2. Okay, so this is nothing but, so this is what we are printing here, ytrain of 25. So you can change these two values and see the image and the corresponding label. Okay, and then image, so this is actually a grayscale image, but this is the color that we will get in Matplotlib show. Okay, so you don't have to think that this is a colored image. This is actually a colored scale image, because this is only one color channel. Okay, and so let's try to analyze some of this labels that we have in this for these images. So image labels, so just some basic analysis of what are all the different values that we have and so on. First, I'll try to print this ytrain shape, ytrain dot shape, and ytest dot shape. Okay, so the first value represents how many values are there in xtrain. So this is nothing but the label for the 60,000 training data images, and this ytest represents the 10,000 labels for the test data. Okay, now let's see what are all the unique values that we have in ytrain and ytest. Okay, so unique value, and another important thing, we can use this data set in order to classify only, like, or in order to recognize only one digit. So you cannot have multiple images, the model may not predict it correctly, because we are training it with only one digit, right? So that's the reason. So unique values in ytrain, and I'm going to use this print. For this, we can use the function np. So we know that np means numpy, right? So there is a function called as unique in numpy, and within this parenthesis you need to mention ytrain. So what this function will does is, it will take this ytrain array. So we know that this is a numpy array, right? So it will take this array, and it will try to find what are all the unique values that we have in this array. So I'll copy all these things, and I'll also print the unique value in ytest as well. Let's see what are all the labels that we have. Okay, ytest. So these are all the unique values. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this is for all the unique values ytrain, and this is all the unique values in ytest. Okay, so the training data and test data images. So this is what is given here. Okay, so y10 is nothing but the digit labels which range from 0 to 9, and all these things are in the form of integers. We can see that here, right? So they are not in the form of floating points. And again, y test also ranges from 0 to 9. So y10 is my training data images and y test is my test data images. Okay, so we can use this label directly. Okay, or you can also perform one-not encoding. So in this case, I'll just use this directly. So in some other deep learning use cases, I'll show you how you can do this one-not encoding on this labels that we have. Okay, so I'll just mention this here. We can use this labels as such, or we can also apply one-not encoding. Okay, so basically what happens in one not encoding is if your label is 0, in that case the first value will be 1. Okay, so the first value will be 1 and all the remaining 9 values will be 0. So let's say that there are like 9 zeros here, 0 0 0 and so on. If the label is 1, your second value will be 1 and all the remaining values will be 0 and so on. So this is what one not encoding is. And let's do this in some other cases. Let's have this label as such in for this one. Okay, so now what we are going to do is, so okay, so and the other thing, as I've told you, we don't have to resize the images as all the images are in the in the dimension 28 command 28. So I'll also mention this here so that you can remember this. So all the images have the same dimensions in this data set. If not, we have to resize all these images. This all the images to a common dimension. Okay, right. Okay, so if you have images with different dimensions, you cannot put that together in a single array, so it won't be compatible, right? So you can create numpy arrays with elements of the same shape. So that's why we have this array. If not, we cannot create this array. So we can say that all these images are in the shape 28 comma 28, and this is also given in this particular documentation here. So all these are 28 into 28 and grayscale images. So these are not colored images, and these have only one color channel. And now what we are going to do is we are going to scale the data that we have, scaling the values. So we know that all the values are in the range of 0 to 255, right? So here also we have, so 0 to 255, which basically tells you the intensity of the colors that we have in this. So instead of having this range from 0 to 255, we can convert this so that we can have the values between 0 to 1. Okay, so I'll show you how we can do this. So this is also called as normalization, so that all the values are in the kind of same range. So this is like very helpful for us, because if the values are large, like 254, 81, 40 and so on, it is hard for the neural network in order to do the calculations, as the number is large, right? So whereas if you convert these numbers into small numbers without changing the information that this data has, all the things becomes easier, and we can also get better prediction. So this is kind of similar to the standard scaling that we have in machine learning, and the normalization that we have to that we used to do. So I'll take this x train. So x train is equal to x train divided by 255. So in most of the cases, if you don't do this, you will probably get a lower accuracy. So in this case, the accuracy may not change, but in most cases that will be the thing. Okay, so it's better to normalize this. So x train by 255 and x test by 255. So what I'm doing here is I'm taking my all the training data and I'm dividing it by 255, and I'm storing it in the same variable called as x train. So you can also give another like name as x train scaled or something like that. Okay, so it's not a thing. So I'm just giving the same name so that there is no confusion and all that. Okay, so I'm taking all this x train, dividing it by 255, and I'm storing it in again this x train, and this x test to this same. So I'm again taking this x test, dividing it by 255 and x test. So let's understand what happens when we do this. So let's say that the number is 0. Okay, so we have like all the values here, right? So each value will be divided by 255. Let's say that there is this value which is 0. So if the value is 0 and I divide it by 255, we know that the answer will be 0, right? And when the value is 255, so we are dividing it by 255 because 255 is the maximum value that can be present in this data. So that's the thing. So there is like nothing more to why we are using this specific thing. So it should be divided by the maximum value that we have. Let's say if the value is 255 and we are dividing it by again 255, now we know that we get the value as 1. So 0 is the minimum value that you have in your training data, and 250 is the maximum value. So the minimum value now you will get is 0 and the maximum value will be 1. So all the other values will be between them. So I'll try to show this to you. So let's say that, sorry. So I'll just open this calculator. And so let's say that we have this value zeros and zeros and all that, right? So we know that if we divide this 0 by 255, so the answer is again 0. So this is my minimum value. So the minimum value that you can have in this is 0. And let's say that if it is 255, we know that when we divide it by 255, this is just very basic math, this is 1. Let's take some other values. Let's say that the value is 40. So if I take 40 and divide it by 255, I will get this value as 0.156 and so on. If I take this value 214, so let's see. So I'm taking this 214 and I'm dividing it by 255. It will be 0.83. So the idea here is all the values will be in the range between 0 and 1. Now it is easier for the neural network to understand the images, to understand the data better. So that's what we are doing here. So let's try to do this. I'll close this one and okay, so I'll remove this and let's run this particular cell. Okay, now we can print this extrain 10. So let's print this 10th image itself. So this won't affect our image because like all the values are changed, right? If you change only like few values, in that case the original data has been compromised, but we are changing all the values. We are just changing the range in which these values are present. So previously you add the range between 0 to 255. Now we are having the values between 0 and 1. So that's the idea. Now if you print this particular value, you can see the values are between, so we have the 0.0. And the values have been converted to floating point, we can see here. So previously in the first row we have all the things as 0 and so on. So we have the value as 0.996 and then we have this 0.3368 and so on. So previously we add the values between 0 and 255. So this is how we can do this normalization, or how we can scale the values between 0 and 1. So instead of having the values between 0 and 255. Okay. And now so these are all the processing that we have to do, and after this we can build our neural network. Okay, so I'll create a text here as building the neural network. So here we won't be using convolutional neural network, so we call this as CNN. So we will build a very simple normal neural network. So in convolutional neural network you have this convolutional layers and so on. So there is a lot of concepts that has to be discussed in this. So we will discuss all these things in the deep learning course, but for now understand that we are not using CNN here. So CNN are like very efficient neural networks that can be used on the image data, and we also have another type of neural networks called as RNN. Okay, so this RNN stands for recurrent neural networks, and this particular neural networks are very helpful when we are working with the text data or audio data and so on. So CNN is widely used for this image recognition, and this RNN for this text recognition and audio recognition things and so on. So here we are not CNN, we are not building CNN, as it may sound a bit complex to you. So we are just building some normal neural network. Okay, so a very basic one. So the first step that we have to do is setting up some layers for our artificial neural network. Okay, so setting up the layers of the neural network, and for this I'll just create a variable as model, and for this model I'm going to use keras.sequential. Okay, so this is why we have imported this keras library. So keras.sequential, so we have to mention the parenthesis and two brackets, square brackets, and within this we have to set up the layers of our neural network. Okay, so keras.sequential. So first thing that I'm going to mention is keras.layers.flatten. So we have seen the use of this flatten in the previous deep learning project itself. So in the previous deep learning, the first deep learning project, we have worked on this breast cancer classification using neural network. So we have seen what is the purpose of this flatten. I'll also explain that to you now. So within this flatten, you have to mention the input shape. So in this case, the input shape is 28, 28. Okay, so what this flatten is, so you cannot feed the data in the form of this matrix. So here we have the data in the form of matrix, right? So 28 into 28. So that means like there are 28 rows and 28 columns are there in this particular image. So each image consists of like 28 rows and 28 images. So you can consider this as a matrix of this shape 28 into 28. So we cannot feed this data in the form of this matrix or this kind of an array. So we have to feed this in a single dimensional array. Okay, so what happens is like instead of having these rows and columns, all the values will be loaded as a single line. Okay, so that's what we do in flatten, and this is how neural networks kind of get the data as input. So this is the purpose of this flattening, and in this flattening we have to mention the input shape. So input shape is nothing but what is your image dimension, and here this is a grayscale image, so we don't mention any numbers here. If you are working on RGB images, so let's say that you are training your neural network on RGB or colored images itself, in that case you have to just mention another value as 3. Okay, so this means that so this is just to tell the model that I'm flattening all the values and all these images are RGB images. Whereas if you just remove this number, so now the model can understand that, okay, these images are grayscale images. Okay, so that's the reason for it. So if you are doing RGB images, just include another 3 years. So first layer is for flattening all the values. So this is just feeding all the values to our neural network. And now we can set some layers for this neural network. Okay, so layers dot dense. So dense is nothing but all the layers in this particular neural network is connected to the neurons in the previous and the next layer. So that is the reason of this particular dense thing. Okay, so we are building this dense neural network, and you can give this value. So I'm setting this value to 50. So 50 is nothing but the number of neurons that we have in this layer. So this is we have this input layer which is the flattening, and then we have this dense layer with 50 neurons. So you can also change this values. So let's discuss later on what the number of neurons we should have and how many layers we should have. So all these things we will discuss later, but for now understand how we can implement the neural network. So let's go into the conceptual part later on. So 50, and we have to mention activation function. So activation is equal to ReLU. So ReLU is one of the widely used activation, and it is a very efficient activation function that we have. So ReLU stands for rectified linear unit. So you can do some research on this part. So this is few neurons will be activated. So activated in the sense their value will be 1, and few neurons will have the value as 0. So when you use the activation as ReLU, so the activation formula kind of changes. If you use sigmoid activation, so that neurons kind of fires differently. So you have this ReLU, sigmoid, and leaker ReLU, and so on. So we will discuss about all these things later on. So here I'm giving this activation as ReLU, and so you have to mention a comma here. Okay, and I'll also create another layer. I'll just copy this one, and I'll create another layer. So I have this input layer where I'm flattening all the values, and then I have this dense layer with 50 neurons, and I have another layer with again 50 neurons, and finally I have an output layer. Okay, so Keras dot layers dot dense. This is just to tell that all these neurons should be connected to the neurons of the previous layer. Okay, so dense 10, and activation is equal to, let's say, sigmoid activation function. Okay, so you can also change this to ReLU. So you can change this ReLU to sigmoid, you can change the sigmoid to ReLU. Your accuracy probably will change, so you can try that out, but this is the thing that I'm taking. So for this first 2 layers I'm taking this ReLU as activation function, which is my rectified linear units, and for this final thing I'm using the sigmoid. So for this output neuron we shouldn't include this comma. Okay, so you can have any number here. So not any number, like you can take the neurons as 70, 75, or 100 or something. So here also you can take a different number of neurons, but this should be 10 here. So what this 10 means is the number of classes that you have in your labels. So in this case, if you check out the labels that we have the values as 0, 1, 2, 3 all the way up to 9. So the total number of values is 10, right? So we are starting from 0 and up to 9. So totally there are 10 values. So that is why we have the number of neurons in the output layer. So this is my output layer as 10. So in the previous deep learning, use case video, the breast cancer classification video, we have add the value as 2 because we just had two classes, right? One is benign and the another one is malignant. So in this case, we have 10 classes, and that's why we have 10 neurons here. So this is the layers of my neural network. So first I have this flattening layer, which is try to convert this matrix into kind of a single dimensional array, which as the values you can consider that all the values will be in the single column. And then we have this another layer with 50 neurons with ReLU activation function. There is another layer. And finally, we have this output layer with 10 neurons. And in this case, we are having the activation function as sigmoid. So you can just interchange it and check how the accuracy is kind of changing. So I'll run this one. And once you have set up this layer, so we are just specifying the specific, basically we are just telling what are all the specifications on neural network. Now we have to compile this. So this part of the code will be compiling the neural network, and for this we have to use this model is nothing but we have loaded this keras.sequential, right? So that's the thing. So model.compile. So there are like few important things that you have to mention. Okay, so you can see, so one is optimizers, and then we have this loss, and then we have this so we have to specify the accuracy, so it will be in the form of metrics. So model.compile loss, the arguments. Okay, so let's see, but the three main important things that you have to mention are this optimizer, loss, and metrics. So here it is. So let's see. So I'm going to mention this optimizers. Again, you have different optimizers are there, and I'm going to choose optimizer is equal to Adam. Okay, so Adam optimizer, and now I'm going to mention the loss. So loss is equal to sparse categorical cross entropy. Sparse categorical. So this is nothing but what is the loss function that you want to build your model on. So loss is equal to sparse categorical entropy, and the other argument is metrics. So what is the metrics that you have? So this is a classification problem. So let's say that the metrics should be accuracy. Okay, so let's try to understand this. So first is optimizer. So we have in machine learning, we know that we have this gradient descent optimizer, right? And the purpose of this optimizer is to determine the most optimum model parameters, right? So if you consider a linear regression, we have the parameters as w and b, and our gradient descent will try to find which is the most optimum parameter. So optimum parameters in the sense, if you choose that value for your parameters, then you will get accurate prediction. Your accuracy values will be more. So similarly, Adam is one kind of optimizer, and then we are specifying this loss function as sparse categorical cross entropy. So here we have seen that we are using this labels as such, right? So this is in the form of kind of integers and simple numbers. Whereas if you convert the labels to one or encoded labels, in that case you have to use the loss function as categorical cross entropy. So this won't work. So this is when you have the labels as simple label encoded values as a 0, 1, 2, 3, and so on. Whereas for one not encoding, you have to remove this sparse underscore. So you have to use categorical cross entropy. And in the metrics, we have this accuracy. So we all know what does this accuracy mean. It is just the number of correct predictions divided by the total number of data points that you have. And you can do some research on what are all the different optimizers that we have in Keras and what are all the different loss functions that we have. Okay, so try to see and try to change this optimizer and see what are all the what is the change in the accuracy that you are getting. Okay, so I'll leave that to you, so you can do some research on the part and check it out. Okay, and I'll run this one. So we are basically compiling our layers, compiling the neural network that we have built with this Adam optimizer with sparse categorical cross entropy as our loss function and metrics as accuracy. So I'll run this one, and now let's train our neural network. So this part will be training the neural network that we have. Okay, so let's say model.fit. So fit is nothing but we know that we use this to train our model, right? So this is similar to how we train our model in machine learning, right? So here we have to give your training data. So training data is nothing but my X train and Y train. So X train is my training data images, and Y train is the label for that corresponding images. So we have to give both of them. Okay, so model.fit, and I'm going to say X train, Y train. So I hope you remember that we have normalized all the values. So all the values will be between 0 and 1 instead of between 0 and 255. So X train and Y train, and other parameter you can mention is epoch. So what is the number of epochs that you want? So I'll mention the epochs as 10. So epochs is nothing but how many times your neural network should go through the data. So each time it will try to change its parameter values, and it will try to give you what is the accuracy and so on. Okay. So this is my first epoch, and so these are all the number of steps there in the epochs. Okay. So this particular neural network is training kind of in a fast manner, right? But in most cases the training takes a very long time. So the reason is here the dimensions of the images are like pretty less, 28 comma 28, right? So here you can see each image is 28 comma 28, so it is not a huge workload for the neural network, so it doesn't require that much computation power. But when you have the images in this shape of 200 comma 200, so actually 200 into 200 is actually a small image, but even all the images are in this particular shape, this model will take a very long time, and it will take a very huge computational resources and so on. So this is just a very small images with 28 into 28 dimensions. So the training has been done quickly. Okay. So you can see how many so what's the time that has been taken for this each steps. And so this is the first epoch, and this is the loss function value for the first epoch, and the accuracy is 91%. So we know that loss function is nothing but the distance between your true value and predicted value. If your loss function value is high, that means your model is not working properly, it is not making good predictions, it is making kind of wrong predictions. So our main goal is to minimize this loss function for a model or for a neural network. So you can see the loss function has been constantly reduced here, and we know what is meant by this accuracy. So the accuracy kind of increases. So 91.3. So what does this means is, like, if you predict the handwritten digits for 100 images, you will get correct predictions for 91 images. So that is what this accuracy means. Like, we can see that loss function decreases, which is what we want, and the accuracy increases in each epoch, and we get the maximum accuracy as 0.989. So which is just equal to 98.9. It's almost 99% accurate, right? So that means out of 100 images, it will give you correct predictions for 99 images. So that's the idea. So this is basically the accuracy on training data. So that is very important. So we have to check it for the test data as well to see whether our neural network has overfitted. So what happens in overfitting is that you will get high accuracy like this for training data, but for test data you will get low accuracy like 50% or 60%. So I'll mention here that the training data accuracy is 98.9%. 98.9%. Okay. And now we are going to evaluate our neural network, right? So this will be accuracy on test data. So this is what we are going to do now. So I'll just make this bold. So this part is nothing but model evaluation. We are going to evaluate our neural network. So I'll mention two values, loss, comma, accuracy, is equal to. So within this model, so model is nothing but we have built this neural network with this keras dot sequential, right? So we have this function dot model dot evaluate, and within this you have to give this x test and y test. Okay, so what happens is, so your model will take this x test alone, and it will give its prediction. Okay, and those predictions will be compared with the true label. So this is my true label, which is y test, or you can also call this as ground truth, the original values that we have. So the model will make predictions, and y test is made true value. So it will compare both of these things, and it will give you what is the accuracy on the test data. Okay, so the test data is something that the model has not seen before, whereas the training data it has already seen. So we cannot take this accuracy as the final one. So it's important that we have to find the accuracy for test data, right? So let's do this. So when you run this model.evaluate, you will get two values. The first value you get is loss, and the second value you get is accuracy. So that's why we have two variables here. And now I'll print my accuracy value. And let's see what is my accuracy. Yeah. Okay. So the loss value is 0.104 and something, and the accuracy value is 0.971, which is like my model is 97% accurate. Okay. So this is the training data accuracy, and I can say that my test data accuracy. I'll just make another text here as my test data accuracy is equal to 97.1%. So 97. 0.1. That means like this is the important accuracy metric that we need. So out of 100 images, your trained neural network can make correct predictions for 97 images. Okay, so we can say that our neural network doesn't overfit. If it does overfitted, in that case, your test data accuracy will be very low. So we know that, right? So we have discussed about this several times in our machine learning use cases and course and so on. Okay, and now what I'm just going to do is I'm going to print the shape of this X test. So print xtest.shape. Okay, so we know that the test dataset contains 10,000 images and each image is of the dimension 28 into 28, right? So I'm going to display the first image. So first data point in the test data, so first data point in xtest, which is my test data, let's say plt dot I am show xtest of 0. So 0 means the index 0. So index 0 means the first image or the first entry or data point. So plt dot show. So I'm going to display that image. plt dot I am show xtest of 0. So the first image that we have in this xtest is this 7. So we can see that this image is 7, right? Now I'm going to print what is the true label for this. Print. So y label is my true values, true labels, y label of 0. So it will be 7. So we know that. Okay, so y label, sorry, it's not y label, it's y test. Sorry. So y test. So 0 is nothing but the first data point. So the first image that I have in this X test is 7, and the corresponding label is, we know that it is stored in this y test. So it is 7, right? Now what we are going to do is we are going to give this X test to our model, and we are going to see what is the prediction made by our model. So it is just this evaluate. So for this evaluate, we have checked the overall accuracy, but I'm going to see the individual predictions made by the model. Okay. So let's create a variable called as ypred. So y test is my true labels, and I'm storing all the predictions made by the model in this variable called as ypred, where ypred stands for y prediction. So we have to mention model.predict. Okay, model.predict x test. Okay, so this will predict the labels for all the 10,000 images, and all the 10,000 labels will be stored in this ypred, which is my prediction value. Now you can see this ypred shape. Ypred.shape. So we know that this also kind of contains 10,000 values, right? Because there are 10,000 images. Okay. Now you can see there is an interesting thing. The value is 10. So we have to understand what does this 10 means. So I'll print the first value in this ypred. So ypred of 0. So this ypred is nothing but, so we are feeding all this xtest to our model, and all the 10,000 labels predictions made by the label has been stored in this ypred. And when I run this will basically give the prediction made for this particular image, this first image, because this is 0, this is 0 as well. So this is the one the true label or the ground truth, and this will tell the predictions made by my model for this particular image. So you can see the value like this. So we totally have 10 values here. So that's why we have the second value as 10. So we have 10,000 labels. I'm just printing in this for only one label. So we have seen what is the significance of this in the breast cancer classification using neural network itself, the first deep learning project itself. The thing is, for machine learning model, when you use this predict, it will return the label value. So whether the label is a 0 or it is 1 or 2 or 3 or so on. Whereas when you use this predict function with this neural network from this Keras neural network, it kind of works differently. It will tell you what is the probability that the value is this one. So if you see this, so 3.51 into e power minus 0.3. So e power minus 0.3, you can just think what would be, without this exponent, you can think about it. So this value is what is the probability that the label is 0. And if you check the second value, this is what is the probability that the value will be 1, and so on. So this is the idea for it. And in order to convert this, so each represents a probability of each label. So first one for 0, second one for 1, third one for 2, and so on. And we have seen that we can convert these values to the labels that we want using np.argmax, right? So we have seen in the previous video. So let's try to do the same thing here. So I'll also mention this, that model.predict. So this is very, very important. So model.predict gives the prediction probability of each class. So each class is nothing but 0 to 9 in this case. So totally we have 10 classes. So you have 10 values here for that particular data point. Okay. So instead of giving that label or the label, it will give this prediction probability. Now we are going to convert this. So this part will be converting the prediction probabilities to class labels. Okay, so it is nothing like for which for which class or which label the value is maximum. So that is the final answer. So out of this we have to find which value is the maximum value. Okay, so if you see here, the maximum value will be for this one, right? So because like all the things have the values as e power minus 0.3 with minus 0.1 and so on. So this is the highest value that we have among all the things. So it is nothing but the one for 7. So this is for 7, for this is for 8, and this is for 9. So this is the maximum value that we have. But now we don't have to do this manually, because we cannot do this manually for this 10,000 images, right? So instead of that we can use this argmax. Okay, so you can just tell that let's say that label for first image, so we are creating this variable, and I'm going to use np.argmax. So this is actually in the form of a numpy array, and when I say this np.argmax, it will tell what is the index of the value that is maximum. So np.argmax, we have to mention this ypred of 0. Okay, so ypred of 0 is nothing but, so this is my ypred 0 values, right? So out of this np.argmax will tell you which value is maximum. Let's run this, and let's also print this one. So print label for first image. So label for first test image. So this test image is nothing but this 7. Okay, so let's see our model has predicted this correctly. So print this one, 7. So this is the value predicted by our model, because we are taking this from ypred. So we are using our model to predict the value of this X test, and we are taking the first image alone. So this is the prediction probability that we got, and we got the value as 7. So what this 7 means is that, so the value in the index 7 is the maximum. So if you count, this is the index 0, this is 1, 2, 3, 4, this is for 5, 6, and 7. So this is my 7th index value. So we start from 0, and this is my 7th value. So this is for 8 and 9. So what this 7 tells is the value in the index 7 is the maximum one. So that is your label. So this is how we can convert this prediction probability into the classes that we have using this argmax. So the role of this argmax is just to tell you the index of the maximum number in your array. So this is a numpy array, and it will tell you the index of the number which is the maximum compared to other values. So here we have done this for this ypred 0 alone, right? Now we are going to do this for all the 10,000 values that we have, so that you get instead of having this probability, you will get the label values. So converting, so it is the same thing. Okay, converting the prediction probability. Okay, so converting the prediction probability to class label for all test data points. Okay, right. So I'm going to create a variable as ypred labels. So ypred will basically contain the probability values, and ypred labels, we are converting them to this labels that we want, the format that we want. So ypred label is equal to np.argmax of I for I in ypred. So this is a simple way of creating a for loop. I'll tell you what this for loop does. Print ypred labels. Okay, right. So what we are doing here is, so we are creating a variable called as ypred labels, and np argmax of I for I in, sorry, so this should be I for I in ypred. So when the for loop runs for the first time, it will take the first value in this ypred. First value in this ypred is nothing but ypred of 0. So this is the first value. So this is the first value that I have in this ypred. So this will be my I. So my I will be ypred of 0. So that will be given to this I, which is my np.argmax. So, basically this step happens each time the for loop runs. So when the for loop runs for the first time, the first image, the argmax will be applied. The second time, for the second image predictions, the argmax will be applied, and so on. So all this prediction probability will be converted into the labels. So let's run this one and see. Okay, so instead of having all this as labels, we have all the values here. So you can also compare how the values are there previously. Okay, so I'll show you. So print ypred. So this is how the values were before. So this is the prediction probability for my first image. This is the prediction probability for my second image, and so on. So this value, this numpy array, has been converted to the value 7. So it is just to tell the digit in that particular image is 7. So the second value, so this is my second entry, and so this happens when the for loop runs for the second time, and the np.argmax value is 2. That means the digit is recognized as 2, and so on. So we are just converting all this probability into classes like this so that it is easier for us to understand. So I'll just delete this one. So this is our final predictions made by our model, whereas the true labels are my y test. So this y test, where is my y test? Okay, so this is my true values, true labels that is given in the data set, and this ypred labels are the ones predicted by my model. Okay, so I'll just mention that here. So y test is my true labels, or you can call this as ground truth. So all the things means the same. Okay, so true labels, and this ypred labels. Okay, so ypred labels represent my predicted labels. Okay, the values predicted by my neural network. Okay, so this is the test data prediction. So that is what this ypred labels is. Now we have already done this evaluation, right? So we have done this evaluation, and we have seen that the accuracy score is 97.1%. There is another interesting evaluation that we can do, which is building the confusion matrix. Let's see how we can build this and how we can infer this confusion matrix. Okay, so I'll create a variable as confusion matrix. So let's just mention this like this. So if you remember, we have already imported this confusion matrix, right? So from tensorflow.math, so tensorflow has this math module, and within that we have this confusion matrix. So this is the function that we are going to use. I'll copy this and paste it here. So I'm going to build the confusion matrix for this predictions. So for this, we have to give the true labels as well as the predicted labels. So we know that true labels are y test and the predicted labels are y test, right? So first you have to mention the true labels. So y test. So how you would calculate the accuracy score in ML. So it is just kind of the same thing. Y test and ypred label. So so the first array should be your true values, and the second thing should be your predicted values. So I'll run this one. So this will build my confusion matrix. You can also print and see this. Okay, so print confusion matrix. Okay, so confusion matrix is not defined. So I misspelled it. Let's paste it here. Okay, so this is the confusion matrix that we have. Now it is hard to understand what these values mean in this format. So now what we can do is we can build a heat map. So we know that we have built heat map several times for this correlation matrix, right, in our regression problems and so on, for the machine learning use cases. So similarly, you can build a heat map with all these values. Okay, so I'm going to, for this purpose, I will be using this Matplotlib, and this is why we have imported the Cbonds library. I think we have never used this pill library, right? Pillow library we haven't used, but it's okay. So now we are going to use the Cbonds and Matplotlib library. So I'm going to say plt.figure. So this is the basic plot on which this heat map is going to be constructed. So here you have to mention what is the size you want for your plot. So this is like pretty simple things. So fixed size, which stands for what is the width and height you want for your plot. I'll mention it as 15 and 7. So with 15 and height as 7, and SNS. So SNS stands for the Cbond library that we have imported, and Cbond has this function called as heat map. So this is used for creating this heat maps. And here you have to mention from which we are going to convert this heat map. So as I've told you, we are going to convert this heat map from the confusion matrix that we have. So we are going to build this based on these values. confusion matrix. So sns.heatmap confusion matrix, and annote is nothing but the annotations for this plot. So annotations is equal to true, and fmt. Okay, so fmt is equal to d. So d is nothing but I'm telling it that all the values should be in the form of integers. So that is the purpose of this. Like if you mention this fmt is equal to %2, that means like two decimal values will be given and so on. But in this case, all the values are integers, so we have to mention this fmt is equal to d, and cmap is equal to blue. Okay, so you shouldn't give blue, the value should be blue. So it is just to set the color, so you can have any colors that you want. So let's create the heat map in blue color here. And now I'm going to give this y label, plt.y label for my heat map. So let's have this true labels in this y label, true labels. I'll explain you what these things means. Just wait for a second. Let's name this x label as predicted labels. Okay, right. So yeah, so let's run this. I think everything is correct. Okay, let's try to understand what this particular heat map means. So if the value is 0 and if the value is small, it is basically represented in a light color, so a very light blue color. And if the value is large, if it is like 800 or if it is 900,000 and so on, it is represented in dark blue color. So this is why we mentioned the C map as blues. If you change it, it will kind of change. So the color of the heat map will change. So just a second. Okay. Now all the values in this diagonal represents the true predictions made by your model. Okay, so all these labels are my true labels, and all these labels are predicted labels, the values predicted by my model. And now let's try to understand what these numbers mean. Okay, so if you see this first box, we have the true label. So you have to see the the y-axis and the x-axis as well. So this is my x-axis where my predicted labels are there. So this is my y-axis where true labels are there. So what this 969 means is like 969 means is like how can I explain you this? So 969 0 images has been correctly predicted to 0. If you see this, the true label, so you have to see the vertical axis here, which is my y-axis, so that will give you the true label. So what this one means is like my true label is 0, but that one particular image, the model has predicted it as 1. So you can see what is the value in this x-axis. Okay, and if you see here, so the true label is 0. Actually, the true label in the sense the digit present in that image is a 0, but it has been predicted as 2. So that is what it means. Like 0 means no images of 0 has been predicted as 3. So that is what the 0 means. And what this 3 means is like there are 3 images, and all those 3 images represented 0, but our model has predicted it as 8. So this is how we can infer this confusion matrix. So it is just to tell you what is the correct predictions made by our model. So 969 means like 969 images of 0 has been correctly predicted to 0. And if you see this 1122 images, 1 images has been correctly predicted to 1, and so on. So all this diagonal means the correct predictions, and all other values represent my false predictions or wrong predictions. And if you want to find this, you just have to see the y-axis for the true labels and x-axis for the predicted labels, and so on. So this is very, very important for us in order to understand like which numbers has been predicted like what. So if you see this one, so it is like a large value, right? So what this means is like 24/9 images has been predicted as 4. So if you see this one, so you have to see y-axis. So true label is 3. So 23 images of 3 has been predicted wrongly as 5. So this is how you can infer this confusion matrix. So it is not easy to infer from this one, but we can kind of put this in an heat map and kind of visualize this like this. Okay, so I hope everyone understood until this part. So this is all about model evaluation. I think like this video is pretty large, but you can learn a lot of things here. And the next, so this is the last part of the video, which is to build the predictive system for our model. So using this trained neural network, we have to build a predictive system. Okay, so what this predictive system is, when you give a new image, so in this case we will give this 3 image. Okay, so when you give this image, the model should predict that it is 3. Okay, so you cannot use like different images of typed images or so on. So if you are training with MNIST images, you have to predict with this image, so that is like obvious, right? So machine learning models and neural network models doesn't know what it is not trained on, so they only know about the data that they have seen. So like so it is just like you cannot train your model on the numbers and you cannot predict alphabets there, right? So similarly, like we have predicted with this MNIST data, so the image that you are going to predict should also be similar to the data that you have trained on. So that's the idea. So just a second. Okay, so now we are going to build this predictive system. So this is one of the interesting part of this code. So building a predictive system. So let's do this stepwise and then we will consolidate all the codes of this predictive system. So first is I'm going to mention input image path. Okay, so input image is nothing but the image which you are going to predict. Okay, so input image path, I'll upload the image here. So I'm just going to this file. So this is where I'm going to import the image. If you're working on your PyCharm or Spider, you have to mention where that particular image has been located. So this is that 3 image MNIST digit.png. So this image has been loaded. So I'll copy the path of this image. Okay, and I'll paste it here. So this is the path of this image. So first I have to read this image and convert it to NumPy array. So we are going to do the processing that we have seen here. Okay, so previously the data has been present as already it has been present as a NumPy array, right? So it is 28 into 28 pixels and so on, whereas this image is not in that format. If you see this image, the dimension is 318 into 318. So we have to convert this dimension and we have to read this to NumPy array, and few processing are there and we will do this. So this is where we will use the things that we have seen here, and I'll create a variable as input image. So input image is equal to cv2 imread. Okay, so cv2 imread, and the first thing that you have to first argument it takes is input image path. Okay, so I'll just copy this. Okay, so input image path, it's not like you have to put it like this. So instead of creating this variable as input image path, you can also copy this path and you can paste it here. So both of them are the same thing. So I just wanted to do this in this way. Okay, so the thing is this imread function cv2 dot, okay, so it's not underscore, it's cv2 dot imread. So this function take this path of the image as the argument or the parameter. Okay, so I'll run this one. Okay, so now you can check the type of this input image. Type of input image, so it will tell it is a NumPy array. So this image, this 3 image, so you can see this here, this 3 image has been converted to a NumPy array. You can see the values here. So I'm going to print this one. So print input image. So this will how this NumPy array will be. Okay, so 0 means black and 250 means white. So with this dots mean like there are several values in between. So I'll just remove this output. Okay, so now you can, again, as I've told you, you can print this image using the cv2 imshow function. So we have this cv2. So this is why we have imported this Google Colab.patches. If you're working in Spider, you can just use cv2.imshow. You don't have to import this one. So Colab doesn't allow cv2.imshow function, as I've told you before. So that's the reason. So cv2 imshow. So this is just to display the image from this NumPy array. cv2 underscore imshow input image. So this is the image that we have, right? And let's check what is the shape of this image. So this is an interesting thing. So now you can see that the image shape is 318, 318, and there is a 3 here. So this is the interesting aspect and the thing that you have to be clear about. So we can see this image is kind of black and white, but actually this has been read in the form of a RGB image. So this has been considered as a colored image. So this is a kind of a crucial thing here. So instead of reading this as a grayscale image, the cv2.imshow is reading this in the form of RGB image. Now the problem is we have trained the images. You can see if we take a single image, where it is. So I'll just go to the image that we have printed. So here, like if you take this two, the shape is 28, 28, whereas in this case the dimension is 318 into 318. And it is 3, so 3 means RGB channel. So we have to convert this image to a grayscale image, and after that we have to resize it. Okay, so these things are there while building this predictive system. I'll create a variable as grayscale, and now we are going to convert this image. Grayscale is equal to cv2 dot CVT color. Okay, so CVT color, and the parameters that we have to mention are input image, comma CV2 dot color RGB to RGB. Okay, sorry. So see color underscore color RGB to grayscale, where it is. Okay, so this is the one. Okay, so what we are doing here is, so CVT is nothing but I'm going to convert the color. So what I'm going to convert this is this input image, this 3. So I'm going to convert this image from RGB to a grayscale image. So this is just basically color conversion. Okay, so let's run this one, and now you can print this input image. Okay, so input image, so we have converted this to grayscale. So we have taken this input image, converted to a grayscale image, and stored this in this particular variable. So I'll mention grayscale dot shape. Sorry, so this should be shape. Okay, now this 3 is not there, right? So what this means is, like, this RGB image is now has been converted to a grayscale image. So that's what we are doing here. And the next step is to resize the image. So this 318 comma 318 should be converted into 28 and 28 dimensional image. Okay, so input image resized, input image resize is equal to cv2 dot resize. Okay, so cv2.resize is the function that we have. So in the previous video we have seen that we can use this pillow library as well. So where it is, so we have imported this image module, and from this we have used this resize function, and this function is from cv2 library. So cv2 also has the same function. So cv2.resize, we have to mention what is the image that you are going to convert. So it is the grayscale image. Okay, so grayscale comma, so here you have to mention what is the dimension that you want to convert. So it's 28 comma 28. Okay, so what I'm doing here is I'm taking this grayscale image and I'm going to convert it to the dimension 28 comma 28, and I'm going to store this in this input image resize. Okay, so let's run this one, and now you can again check the shape of this input image resized one. Okay, so input image resize dot shape. So previously it had 318 comma 318 as your size, and now it has been converted into 28 comma 28, because this is the size that is compatible with the neural network that we have built. So you can see here, so we have mentioned that the input shape is 28 comma 28. So the model expects the image to be in this particular dimension, in this shape. So that's the reason we are doing this particular step. Okay, so you can also show this image. I'll also use this cv2 function again, cv2.imshow. Now let's see how the image is looking like. cv2 underscore imshow, and now I'm going to show this input image resized. Yeah, so previously the dimension of the image is like this, and now it has been like shrunk to this. So this is the dimension before, so 28 comma 20. So this is a 28 comma 28 pixel image. Okay, so next step is like so next part is the other thing that we did is scale the image. So we have did this normalization part, right, where it is this 25. Yeah, so this 255. So we have converted all the image. So previously the values between 0 and 255, right? Now it has been converted to 0, between values are between 0 and 1. So how we did that is by dividing all the value by 255, right? So we have to do that here as well. So this is like very, very important. So what are all the things that you did for your training data should be done for this as well. So this part will be I'll just take this as input image resize itself. So I'm not changing the name. So input image resize is equal to input image resize divided by 255. Okay, so now all the values should be scaled, and all the values should be between 0 and 1. Okay, and there is another important step. So before predicting, there is only one more step that is pending here, which is to reshape. Okay, so image reshape is equal to np dot reshape input image resized. I'll explain you what is the necessity of this, comma, and here I have to mention 1 comma 28 comma 28. Okay, so if you have seen my other videos, my previous machine learning use cases videos, when we are building a predictive system, first we will take all the values and we will kind of reshape it to 1 comma minus 1. So the reason for doing this is to tell the machine learning model that I am predicting the label for only one data point, right? So we have done this np.reshape 1 comma minus 1. So we call that as input data reshape. Similarly, we have to tell the neural network that I am going to predict the value for only one image. I'm not giving you 10,000 images or 60,000 images, and I'm giving you only one image, and you have to predict the label for this one image alone. So that is what we do using this reshape. So if you have some doubts, you can copy this input image resize, and you can check this shape, not type. So this type is nothing but numpy array. So this is not in the form of images. So CVT I am sure will basically convert the numpy array to an image. So this is actually in the form of a numpy array. So you can see this. Now we are taking this numpy array and we are reshaping it. Okay, so it is just similar to that 1 comma minus 1. So we have to understand why we are giving this particular value. So I'm creating a new variable called as image reshape, and I'm using this numpy. So we have the same reshape function, and we have to pass the image that we are reshaping. So this is the image that I have after resizing and after scaling down the values. And the second argument that I pass is 1 comma 28 comma 28. So what this means is I am going to predict the value for only one image, and the dimension of this image is 28 comma 28. So that's what we are doing here. So there is like nothing complicated in this. So I'm taking one image 28 comma 28. If I'm let's say predicting for 10 images, I have to mention that 10 comma 28 comma 28. So here I'm taking only one image, which is 3, right? And another thing, if you are working with RGB images completely, so let's say that you are training your neural network with RGB images and you're predicting for RGB images, in this case you have to include a 3 year. So this is a grayscale image, so we don't have to include anything here. So this is a very important step. So if you don't do this, so your prediction will throw error. Okay, so that's the thing. And let's run this one. And again, so here as well, if you're, I think I have mentioned this already. So if you're training your neural network with RGB image, so along with this image dimension, you have to mention as 3. So here it is grayscale image, so it is not necessary here. And yeah, so it is this part is for reshaping. So I'll run this one, and now we can use our model to predict. Okay, so I'll create this variable as input prediction. So input prediction is equal to model dot predict image reshape. So this is the final array, the processed image that we are going to feed. And let's also print this prediction. So print input prediction. So we are predicting the value for one image, and we are printing it. Let's see. Okay, so we have successfully printed it. So this is the value. So we know that this is the probability value, right, for each classes. Now let's again use this np.argmax in order to find the label. So I'll name this as input pred label. So it is nothing but input prediction label is equal to np.argmax of input prediction. So I'm taking this input prediction array, and I'm going to find which is the highest value. So that's the idea. So let's run this one, and now let's print this input data prediction, sorry, input pred label. So now let's see what is the model is predicting. Yeah, so now the model has predicted correctly that this image represents 3. So we have successfully printed it. So if you see here, this is for 0, this is for 1, 2, 3. So this is the maximum value that we have, right? So the model has predicted correctly. So this is nothing but plus 1. So all the other values are e power minus 3, minus 8, and so on. So the model has correctly predicted that the value is 3. So we are predicting this from model. So this model is nothing but the neural network that we have built. So this is how you can build a predictive system. I'll just combine all this code so that it is in the in a single shell. So the same, so I'll just put a text here. So we are not going to do anything new. So predictive system, so I'm just going to combine all this code for this predictive system. And the first thing is input image path, right? So input image path, so this is the first thing that I want. Yeah, this to itself here. So input image path. And now, so instead of hard coding this, instead of mentioning the path here itself, I'm going to create an input function. So input of path of the image to be predicted. Okay, let's see how this kind of works. Path of the image to be predicted. And then, so once we give this prediction, so what happens is like this will show this particular statement, and the user has to specify the path of the image, and after that will be loaded. So you can give different paths or different images each time you run. So that's the idea. So input image cv2.imread input image path, And the next thing is, let's also show the image. Okay, so once the user has mentioned the path, let's also show the image that is present there. Put image path, so show the image. And the next step is to convert the images to grayscale image, right? So this is important. Grayscale cv2.cvt color, and then input image resize. So all the things should be done. So this is my resizing thing. Okay, input image resize. And the next thing that I have to do is reshape it. Sorry, so we have to do this as well, right? So we have to scale the values down. So 255, and the next thing will be reshaping. So reshape all the values. So this is for predicting only one image, and this is my input prediction. So we don't have to print this prediction, so we just have to find the label. So I'll just remove this. Finally, my input prediction label. Okay, so input pred label, which is the np.argmax of input prediction. And finally, we can print that the handwritten images. So the handwritten digit is recognized as, we can put this input pred label. Okay, so what we are basically doing here is, so first when this line executes, so it will ask the user for the path of the image file. After that, that image will be read using the cv2.imread function into the variable called as input image, and we will also display the image to the user itself. After that, we will convert the image to a grayscale image, and then we have to resize the image to the default value that we are taking, which is 28,28, and after that we have to scale the values down so that the values are between 0 and 1 by dividing it by 255. And then we are resizing the image. As I've told you, we have to tell the neural network that I'm not predicting for 10 labels, I'm predicting for one label. And then we are using this model.predict. So this is for predicting the values, and once we have this prediction, we know that it will be in the form of probability. So we have to convert this using this np.argmax, and finally it will print your labels. Let's see how this works. So I'll run this one. So here you have to give the path of the image file which you want to predict. Okay, so I'll go to the files, I copy the path of the image that I want to predict, and I paste it here. Let's see how this is working. So once I give the path of the image, you can see here, so I have given the path of this image here. So this code will display the image that has been given, and it will give this statement that the handwritten digit is recognized as 3. So in this path, so when you run this, instead of, you can have multiple images. I mean, like, you cannot give multiple images at once, but you can give different images each time you run this. Okay, so you can take another MNIST image and you can give this value. So it will display the image and show the result. So the process that are happening are, first it should read the image, it should convert it to grayscale, then resize it and divide it by 255, then reshape the image and make the prediction and print the print statement. So that's it for this video. I know that this is a very long video, but this will be like very useful for you, moving on to the image recognition projects that you have. I'll just give a quick recap so that you kind of remember all the things that we have done. So first part is just importing all the necessary libraries. So we have Numpy, Matplotlib, Cbounds, and so on, and we have this deep learning libraries, TensorFlow, Keras, and so on, and confusion metrics for building our confusion metrics and displaying it in heat map. So we know that the data is in the form of MNIST. So but the thing is, it won't be in this format every time. So the actual data that we have will be in folders. So you will be given a folder, and that particular folder will contain 10,000 images or 20,000 images. So you have to do all the processing, and then you have to convert it to test image and train image and so on, but we will work on that later. So here we have the dataset in this keras.datasets itself in that module. So we have loaded the dataset, and we have got this training data and test data separately, and we have seen that there are 60,000 training images and 10,000 test images, and this is the image dimension, and we know that all the images are in the form of grayscale. So we have printed and seen what are all the values, and we have taken like one image and we have printed it, and we have also seen the corresponding label. So all the values are correct, and we have seen that this is the count of the labels we have for training images and test images, and we have seen what are all the unique labels that we have, and we have found that there are 10 labels, right? And then we have scaled the values so that the values are between 0 to 1. So before we had the values between 0 to 250, now we have the values between 0 and 1. So that is the next step. And later we have seen so how the values has been changed and so on. So this is not that much important. So this is the important part, which is building the neural network. So we have built a very simple neural network where you have to create this flatten layer, and you have mentioned the input shape. So input shape is nothing but the dimension of the image, and then we have built some layers for this neural network with 50 neurons, and we have mentioned the activation function as renew, and the final output layer. So this is my output layer with 10 neurons because we have 10 classes 0 to 9, and then we have compiled with Adam optimizer, and the loss function as sparse categorical cross entropy, and metrics as accuracy. So that's why you are getting this accuracy value here, and we have fitted. So this is the training of neural network, and we have trained it with 10 epochs, and we have found that the training data accuracy is 99.9, which is almost 99% accuracy. And then we have calculated the test data accuracy, and the next part is taking the first image of the test data, and we are passing it to our model, and we are asking it to predict, and we are converting this probability into label using this np.argmax, so it is predicted correctly, and we are doing this for all the values that we have, and this is the final labels that we are getting. And using this, we are building the confusion matrix, and we are visualizing this to see how many correct predictions are there and how many wrong predictions are there for each classes. And later, the important part of building a predictive system, where we have done all these things. So when you give the path of the image, so it will first show the image to the user, and it will uh, read the image in the form of numpy array, convert it to grayscale, resize it, divided by 255, reshape it, and finally make the predictions using neural network and apply Rmax in order to give the result. So I hope everyone has everyone understood all the things that we have covered in this video. So please practice all the things. So this is a very interesting use case. So try to do all the things. It's okay if you kind of just looking at the code and you're practicing it by yourself. That's not an issue. So you will get better by practicing. So I suggest that you have to practice all the codes that has been done in this particular video. And yeah, so that's it from my side, and I'll see you in the next upload. Thanks for watching.